I want to hear about the event you went to that we talked about briefly.
Remind me, it's been so much. When did we talk? April, May, June? When was that?
The last time we talked was maybe June, but I know you were at a conference that you had that you were excited about. You mentioned, and it was about one of the topics we chatted about.
Got it. Okay, it's coming back to me. So this was after my trip to India.
Yes, yeah, exactly. After you
Fine.
went, I think you went to Bangalore.
Pune, Mumbai, New Delhi.
Okay, yeah, it was after that trip that you had.
Okay, good.
Yeah, you're a busy man. You got a lot going on. It's hard to remember.
That trip itself was very eventful. I think I had 7 or 8, maybe 10 speaking engagements. Then coming back. Okay, so we talked after I came back. Then I went to so we have a tradition in particle physics, what we call a community exercise. So it's more than just some kind of, it's a decadal affair, right? Every 10 years, roughly. Last time was 2013, not 22. And it's not just a bonding exercise. It's a soul searching, I think is the best way to put it. So many of us in the US will get together in one place. Historically, 20 years ago, it used to be at Snowmass. So Snowmass is a ski resort close to Aspen. So beautiful place. But of course, we would go in the summer, so it would be much cheaper. Mostly it was empty. So we would all arrive at this sort of hillside place. You would get a bargain on the hotels and everything because it was the summertime. And so for some time, we would all get together and think hard about what is the physics we've done? What directions is that pointing to? What are the indications from all the physics we've done that the next set of priorities should be this kind of physics? We should look at this kind of potential new collider. That's where the puzzles could be explored there. Maybe the next set of discoveries could be done here. Or should we do in the other kind of experiment? Or should we look at the particles coming up at us from the sky? All the different options of different ways in which particle physics is done. And everybody would come with their studies. I mean, it would be quantitative. It wouldn't just be sitting and talking around. People would write down their stuff in 2-page, 4-page things. These would all get compiled. People would then be, come informed, see what everybody else is going to talk about, then listen to their talks. And then coffee breaks, lunch, dinner, all this time, people would sit and say, I like that. Maybe that's a good idea, and so on. And so eventually it would all that would get recompiled through all our sessions. People would take notes. Some people would be designated to take notes. And at the end of it, you would come out and say, looks like the community has done a bunch of quantitative soul searching about where the field is, where they could be going, where the next 10 decades, next 10 years would sort of bring the biggest reward, biggest bang for the buck. What type of scientific investment should we be making in which particular kinds of experiments? What are the challenges those face? And then it would go into, well, if we were to solve this and this and this technical challenge, we could do these kinds of experiments where the next big revelations about nature would show up. That's our best bet. Let's go write it all down. We can all look at it. Anybody who gives us funding can now look at it, and that would be the voice of the community. And then people can go and debate the money and think of all. So that traditionally got called a Snowmass exercise because it was held close to Aspen.
This discussion.
For the last couple of iterations, we didn't go to Snowmass. The best I can say is that maybe, even though it's a very nice place and it wasn't significantly more expensive than any other because you found just the right deals, right? When the hotels were sort of empty and something.
Yeah.
But the feeling was maybe it sends a perception that you're off, going to some resort town or something, and we are not here to spend money. In fact, we want to be as stingy as possible on the public dime.
So is that where the forefront of particle physics is being talked about? Is that the tippity top, pretty much, would you say?
I would say it's the single largest, all-encompassing workshop forum meeting.
Okay, so the newest ideas are being talked about in these meetings.
It's much more. It used to be called the workshop. It used to be called the community planning workshop.
Yeah.
Where you would literally have having done a lot of preliminary work, run your calculations, run your estimates, run your simulations.
Yeah.
And then based on the feedback you would get early in the workshop, you were supposed to literally burn the midnight oil, which is what happens.
Yeah.
We're often up there late at night over coffee or something.
Yeah.
Tuning up the calculations, trying to answer the questions from today's workshop session.
Yeah.
So come back tomorrow and say, okay, there was a good question. We need to make sure our estimate on that is as good as we want to. So we've done some more work, and here's the answer to your question. So it would be literally be interactive.
Mm-hmm.
So that's different from other big meetings we have, which are literally conferences,
Mm-hmm.
where your slides are already made. It's like a
Right.
presentation, and you're just going session after session, result after result.
Yeah.
But you're not typically at a conference. You're discussing the results that people have achieved, but you're not engaged in an active debate about what does that mean for what we should do next.
Right. It's a one-way street. It's not collaborative.
Yeah.
And what you just went to, and this more collaborative experience is how intellectuals through the last thousands of years have been talking.
Yeah.
It's really what this podcast is about. But it's very. Is that private individuals or academic individuals, or both?
It's open to the whole community. I mean, it's organized by the US particle physics community.
Okay.
But it's open to everybody. So the entire world knows what the agenda is, and you can come and make your case and sit and listen to us and so forth. So I would say it's 90% US, 10% international people join us to listen what we are thinking.
Germany, I'm assuming, is
everybody. Europeans, Japanese, China, India. I mean, depends on people's travel budget and time and so on.
Mm-hmm.
And it's about 10 to 15 days. It's almost 2 weeks. So everybody can't take that much time off. So people come for maybe the beginning, maybe the end, maybe the days in which their particular topic is being discussed.
Yep.
So, and it doesn't happen every year, right? Conferences are happening every year, but this happens every 10 years or so. And this will then be the fodder on which the government agencies are going to chew upon for a year, 2 years, to say, okay, every option that you guys want to think about, you talked about, you wrote it all down. So there's a ton of documentation written like this. And everybody has a chance to speak. It's not private, closed door or anything, right? Where actual decisions are being made. This is just open forum. It's like the old Socratic seminar, right?
Mm-hmm.
You made a point. Okay, you have a counterpoint. Raise your hand, say it. People can debate it. Let them argue. Somebody will take notes. Write it down. It will be always in the public record. Then slowly it converges into, okay, let's form a committee of experts, 30 people. Let them read through this for a year. Let them bring in the individual authors of this documentation. Why do you think your experiment is going to work? Have you thought about this particular technological challenge, this, that? Tell us about your cost estimate. What sort of physics do you think it could deliver? Has that physics already been covered by some other set of experiments that has happened? So maybe that's not such a good way forward anymore. Maybe we should put our bet somewhere else. So this committee will then pore over this now for another year or so. And then ultimately the funding agencies will extract from this an essence of where the field is wanting to put its bets.
Okay.
And everybody doesn't win. I mean, obviously all proposals do not get funded.
Mm-hmm.
We will try to, of course, make it as merit-based as possible. But even there, merit is a single nice word to say, but there is risks to be technological risk, cost risk. Some proposals are high risk, high return. It may find nothing, but if it does click, it could find the next big thing. Others are smaller scale. Okay, if no new physics shows up there, it's still fine. It'll be an excellent training ground. It's not that expensive. The technology is sort of almost in hand. It's a smaller time scale. It's not a 20-year project being proposed. It may be a 5-year. So the dimensions are cost, risk of all kinds, technical, potential impact. And in their wisdom, this committee will bring back some of the authors of these things and eventually write up something. But that committee is reporting to the federal funding agencies. This particular exercise is open door. So you got to listen to everybody, but of course, you can't have 700 people sitting and making a decision. In the end, you got to have 30 people, having heard everybody, sit down and make some recommendation. Ultimately, again, this is not a decision. It makes recommendations to the funding agencies. And of course, finally, the funding agencies report to Congress. So ultimately, it's ultimately a congressional decision of what they want to fund.
I see.
But how do they get informed? So they have to get informed by funneling all the information from the entire community through a smaller group, through an eventually even smaller group. And somebody's going to put something in front of the House Science Committee or whichever committee eventually is going to provide
Gotcha.
out. So most of the people attending here are academics.
Mhm.
It's open to industry people.
Okay.
Now, you know that our field is mostly fundamental science of, the big questions of nature. What happened after the Big Bang? Why
Right.
is the Higgs boson the way it is? What's dark matter? What's dark energy?
Mhm.
So a typical research-oriented corporation isn't directly coupled to this kind of research. Some of them are interested in the technological needs that we have. So if a particular type of experiment or a particular type of accelerator is going to need a special kind of magnet or a special kind of radio frequency gadget or some special kind of superconducting device, then companies in that business will often send their representatives. Just listen to what they're talking about. Maybe there's a collaborative option there. They're going to fulfill our needs. Eventually, the large scale stuff could be done by them. Maybe they'll supply the material, something.
Mhm.
But that's typically a small number. I mean, unlike some quantum computing conference or somebody where huge industrial input will be there, at this stage, we tend not to have a lot of industrial participants.
Got it.
They want to see what we decide, and then whatever our technological needs are, at that point, they'll see what type of partnerships are possible.
Has nuclear energy been on your mind at all? There's been a lot of talk of nuclear energy, and I'm just curious if you guys talked about that at the conference at all?
As a spin-off, so there is one particular aspect of nuclear energy which does get discussed a small fraction of the time, because one of the tools of our trade is a particular kind of very high intensity accelerator. So we have different kinds of accelerators.
Yep.
Some of them focus on very high energy.
Mm-hmm.
So in our language, we call that the energy frontier. So the LHC, for example, is the energy frontier machine. Before that, it was the Fermilab's Tevatron, is the energy frontier machine. So there is talk about, could you build a machine 5 times bigger than the LHC, up to 10 times the energy? That's one type of talk. The other is, what about processes which are happening at lower energies? The underlying physics in them is very high energy physics. So by quantum mechanics, when you try to see a high energy physics process in a low energy experiment, it has to be rare. So you can compute why that ratio of energies means the process will be very rare. And a rare process means you have to have an extremely intense beam. So it's not a high energy beam necessarily, but it's extremely intense.
Okay, what's the difference?
One is, so think of a proton, right? So your typical beam particle, proton.
Yep.
How much energy do you give to each proton is one variable you can try to control. The other is how many protons are you accelerating?
I see. So hitting light off the proton is one thing. How many protons you're hitting is the other.
Yeah. So high energy machine, high energy accelerator emphasizes or prioritizes the first objective, the energy for a given proton. Try to make that as high as you can within technological bounds, cost bounds, and so forth. And within that envelope, of course, as many as possible you can get, but your primary goal is the energy per proton. The other kind, the energy is no big deal. It's an energy that has been achieved 30 years ago. The frontier or the challenge is, instead of every second or every minute, a billion protons coming at you, can you make 1 trillion protons coming at you? So it's the number of protons at some energy that we've achieved long ago. So the energy is not the technical challenge anymore. We've known how to do that energy for 30 years. But the number of protons being accelerated at that energy, can that be 1,000 times more than the last time? So what's the constraint here? Why not? There are plenty of protons around, just throw more at them. Now the issue is the total amount of power. So if you do the math, it's the energy per proton times the number of protons is the total power in the beam. So now the limit is, we're talking next about 1 megawatt beam. So 1 megawatt, your typical bulb is 50 watts. So you take the ratio, you can sort of see how many light bulbs of energy is literally in that little pencil beam coming along. And to create that much energy in the beam itself, how much energy do you have to pump in? Because the efficiency of the process is certainly not 100%. It's much lower than that. So you have to put in a lot more energy to get that much energy in the beam itself. So we want such machines for a particular set of experiments where the process you're trying to observe is extremely rare. So now you ask, is there any use of this second type of machine somewhere directly for community usage, right? Economic use, commercial use? And there is one. And so in this context, the question you ask gets discussed. There are two things about nuclear power. There is the traditional reactor, right? So you take uranium, something, you purify it a little bit, you make a whole bunch of it, you stick it in the reactor, you leave it there for 5 years, and the uranium turns into this, that, or the other, and in the end, at some point, the particular reaction that the reactor is using runs out. But now there's tons and tons of radioactive stuff in that reactor core, but that particular type of reactor can't use that anymore. So this is the spent nuclear fuel issue. So you have to take that whole core out 5 years later. You stick it somewhere underground or in a big tank of water, and you just don't go near it, and you just let it sit there, and it's going to stay radioactive for a very long time. Then you put the next core in, and then that operates for 5 years. So the question is, what do you do with these old cores that are radioactively hot sitting around? One idea has shown up for some time, which is, hey, let's take our high intensity proton beams, the one we were talking about, the megawatt beam, and shoot it into this spent nuclear fuel. So it's no longer nuclear fuel, you call it nuclear waste.
It's decayed though. So that's, how is it?
Some part of it has decayed, but a lot of it hasn't decayed.
Okay.
it's sitting there in a way that you can't control anymore. So the whole point of the initial reaction, what you call the fuel, before it becomes the waste, is it has a particular kind of reaction that we call nuclear fission. And the great thing about nuclear fission, discovered by Enrico Fermi under the University of Chicago in 1939, is that it's controllable. It's a chain reaction. It produces neutrons, and those neutrons then create more nuclear breakup, and that produces more neutrons. So the neutrons coming out are constantly creating more reactions, and so that's how you produce the energy. But you can put material into the core which will absorb the neutrons. So the neutrons are like a catalyst. If you take away the neutrons, the whole reactor slows down. So this is how you can control the reactor. You have to be able to control the reactor. Right? If you let the neutrons out, the reactor will fire up. And if you absorb the neutrons and take them away, then the reactor cools down. So now you have a controllable reactor, which is what a utility company has to have. The spent fuel is still radioactive, but it no longer has this particular controllable reaction available. That reaction is done. Some other reaction is going on, so it's still radioactive. The trouble is the remaining reactions are not this kind of chain reaction that you can control. So it's a low rate, not enough to make it economically viable to produce energy from, but it's still, for safety purpose, sufficiently radioactive that you can't do anything with it. You can't go near it. You can't just stick it in the ground and say, okay, fine, it's safe. It's not safe for a long, long time. But the high energy yielding reactions that you can control, those are the two things about the reactor that you want. It's high energy yield over a small amount of time and controllable. Those two aspects are done. So you can't, it's not worth leaving it in your reactor. You'll get very little power from this time on, but it'll just be radioactive for a long time. So you basically just take it out and leave it underwater somewhere in a big swimming pool. This high energy or high intensity proton beam has a way of inducing new kinds of reactions in the spent material. So it transforms that nuclear waste into other stuff. And that other stuff can now produce more energy. So if you do the math, you find that the first reaction that a typical nuclear reactor is exploiting, that first reaction has really only extracted about 5% of the total energy you can use. But it's the 5% that we know how to use, so that's the part you get. The remaining 95 is sitting there, but the typical reactor is not able to use the other 95. So even though it's waste, it's kind of potentially useful waste, but we don't know what to do with it. This idea says you hit it with this intense proton beam, the remaining 95 will also become useful. So it's like a second, it's like a recycling almost. What you thought you couldn't use anymore, you make it useful again by hitting it with this proton beam. And the idea is this is controllable again, because if you turn the proton beam off, then this recycling process stops. And if you turn the proton beam on, then the recycling thing starts again. So it's a way of getting two goals done. A lot of the available energy in that nuclear material is used in this second stage. And secondly, what used to be waste that had to sit around is now becoming it's no longer waste. So in some sense, you can burn it up. You're burning it up faster. So people are doing these calculations. How much energy do you have to put into the proton beam initially to fire up this second kind of reactor? And how much energy can you get out of this so-called waste, which is no longer waste? It's kind of useful now. And does the economics work out? And if this is shown to be doable, we could make the case that the particle physics tool that we are developing for our uses is also usable as a green energy source. So you can see how it suddenly becomes like a fantastic thing, right? You have a research application for it, and therefore we'll keep developing the beam technology and make it better. And somewhere out there is a company that's using our existing beam technology, also solving the waste problem at the same time from the other kind of reactor.
Yeah.
So if we are, which we have to be, let's put it this way, not that if we are serious, we have to be serious about the green energy solutions. We absolutely have to be.
Well, not only the fact that it's green, it's clean, but it's unlimited. It's forever. We really can't run out of nuclear, right?
Basically, if you multiply the amount of nuclear power we can make now based on the nuclear materials you're digging out of the earth, and if you say, I'm only using 5% of it with all the technology you've developed, and this technology can give me another 25, 30, 40%, then basically the same amount of nuclear mining that we have to do, that stuff that you've already dug out, you've already purified it, it's already sitting there in the core. If you get 5 times more out of it, the US, I think the US electricity grid is about 20% nuclear now. Without any more investments in nuclear processing, if you just deploy these beam-based reactors, you could take our current energy usage and basically satisfy 100% of it with just this. Now, the future is going to need more than what we are using today. We always use more in the future. But now you supplement it with another whole bunch of solar and another whole bunch of wind, maybe offshore wind, a lot of land in the US. I hear about Massachusetts and North Carolina coasts being quite perfect for wind turbines being deployed. They're talking about 20 megawatt wind turbines now. So take the appropriate mix of wind, solar, which is seasonal, day and night for solar. Wind is generally stable day and night, is actually better at night. But summer versus winter, winds can change. So if you add up wind and solar, you can't guarantee that you can get all the energy you need all the time. Sometimes you have a surplus, and then sometimes you might be short.
Right, that's the issue. Yeah.
So now if you have this kind of second phase beam-based reactors, and you can control those, you can turn the beam on and off, literally by a button. You can fire them up at will, you can ram them out at will. There's effectively an infinite amount of power there. It's just how many reactors do you want to build? It's the costing of it, and it's the investment upfront of it.
Right.
We could have a way out and basically have no fossil fuels for the electricity grid, at least. I mean, heating houses and transportation,
right,
that's a different issue. Transportation, hopefully we get electric vehicles all the time.
Yep.
Heating, third thing. So let's not talk about that. But to wrap up this issue, this accelerator technology, there are conversations going on about it. So I have a colleague from Fermilab who is now in US Congress, actually. And I had a long chat with him yesterday, coincidentally. So I was asking about how are we going to make the whole US grid completely green? What's the politics like? What's the corporate involvement like? How is the incentives going to come along? What do we do with all the investment in fossil fuel generating electricity? Lots of people work there. Lots of companies own things. How do you make a transition? So he really picked up on this point. He's a Fermilab ex-scientist, so he knows the technology.
Yep, that's important.
And he is in fact saying, let's make sure that all the spent fuel from all the reactors, which today seems like a hassle, what do you do with the last 10 or 20 years of spent nuclear fuel sitting in my backyard? Let's turn that into an asset. Let's think about it as an asset waiting to be used. While we think hard about how these beam-based reactors might work, how do you make them economically feasible and so on? Because who knows, that could be a huge part of the solution in the future. So this aspect is not lost on us when we come back to the particle physics and, what would it take to build this kind of beams? Is there any long-term use of developing this technology? The answer is there could very well be.
Mm.
This is not how we argue for our science, because we are only making the discoveries, the case for the discoveries you could make with one or two of such beams in the US. But if you're able to develop them, operate them stably, show a 10-year track record, no incidents, nicely controlled, safety rules, everything is working out.
Yeah.
Maybe at the next Snowmass, we should invite a bunch of nuclear energy people, nuclear engineers and so on, and say, look, we've deployed such a beam. It's doing the science for us. But how about commercialization of this? I mean, it won't be just a conversation with particle physics. We'll need buy-in from a lot of other places, and we would need our political, political framework needs to be supportive of this.
Right. That's the beauty of the U.S. We have such a strong private sector that creates the capitalism creates an amazing companies, but of course those people need to talk to you guys. So that bridge needs to be created, and then we get from 0 to 1.
Yeah, there we probably need help. The word needs to get out there. We are up to interesting things. Come and see. Maybe this particular thing actually could be a solution to our social needs, economic needs. Right. And by the way, you guys could turn a profit out of this. You'll have to make some investment, and we can tell you how much investment it took. Mm-hmm. For our field, $1 billion project is a major deal. I mean, it takes years and years to come to a consensus that that's the kind of investment we want to make in a particular machine infrastructure and so on. And then it better do physics for us for another 15, 20 years.
Wow. Yeah.
But now you think of a single commercial 5 gigawatt nuclear power plant, for example, $40 billion.
Right.
One nuclear power plant. I think there's 20 or 30, I don't know how many are operating in the US now. I know at least one at Braidwood in Illinois. Illinois has quite a few of them.
Interesting. I didn't know that.
I know there's one, about 20 miles from Duke. If I go up for a hike on a little hill behind, you can see it over the trees.
Oh, really?
Yeah, and it's Progress Energy or Duke Energy. I don't know. One of those companies runs it. And we happen to know somebody who works in Progress Energy. They said we can arrange a tour. So
Yeah. So 40 billion.
These things are around, and a new one costs 30, 40 times more than one of our big deal expensive projects in our field.
Right. But the science to get there costs so much.
Yes.
Right. And so that cycle's broken is what I'm trying to say. I think it needs to not be broken. Not how much it costs you guys to do the work, but the money, because for you to get that money to do the work, that's the part. For these businesses, it's easy. It's just it's private equity, it's investing.
Yes. That's right. It's true. We have to make a very carefully planned, very elaborately described case for $1 billion of public funding.
Taxpayer money, right?
Taxpayer money. We have to be very careful with it. But as you said, corporations in the US, somebody is building a $20, $30 billion silicon processing facility here. I mean, it's a big deal for them too.
Yeah. Or
a battery plant, GM or somebody is building a battery plant in Tennessee or somewhere. The other day I heard. It took $20, $30 billion. Okay. One of these companies Apple decides to build a new office in Cupertino or something, the whole round new building.
Yeah.
I said, what's the price tag At least in the public domain, $5 billion what I read. One company just builds an office building for themselves.
Yeah.
And it's costing 5 times our expensive projects. So you're right. There's an enormous amount of investable resource
Yeah.
in the corporate sector. It's a
Right.
$30 trillion a year US economy. It's $30 trillion.
Yeah.
And we are talking about one of these beam things costing maybe $1 to $2 billion.
Yeah.
So if it works,
Mm-hmm.
so I think my congressperson friend he's known this for a long time. I am happy, for example, that such a solution, even though it's got the word nuclear and beams and radiation in it,
Yeah.
that he is saying it openly in front of 30, 40 people.
Yes.
That the whole politically safe kind of thing about, oh, let's not say the word nuclear. Oh, that probably scares a lot of people. I'm glad we say the things that should be said. Risks have to be evaluated. A lot of very smart engineers out there who know exactly how to deal with every kind of risk.
Yep.
So let's not just get scared by words. And in fact, people have said that such a kind of reactor is in some ways safer because it doesn't have the chain reaction problem that the 50-year-old reactor technology, the current one that's out there.
Right.
That reactor, if you're not able to control, the chain reaction goes out of control.
Right.
And then you have this Chernobyl-like meltdown once in a while. Once in 20 years, 30 years, it's happening. So that's what's creating the scare, which is fair enough.
Yeah.
This has that other big attribute that the kind of reaction you're exploiting now, the nuclear process, is not a chain reaction. It's not self-sustaining. It only happens when the protons are hitting your target.
I see.
And so all you have to do literally is drop a brick, a big brick, but you can literally drop a brick in the path of the beam, and the reaction stops.
Just shut the beam off.
Just shut the beam off. And there are 5 easy ways to shut the beam off, right? So,
Right. And so, yeah, the amount of fail safes around this new tech, if it was developed, would be great. We wouldn't have to worry. But there is a stigma around nuclear, around
that's the problem.
radiation. But I think it's also just an innate misunderstanding of the people that aren't scientists, right? Government officials and scientists and these smart people that are going to fund it and build it, they know what they're making. But we only see the people on the ground, normal Joe Schmoes. They just hear the words and they panic. So that's a shame. But
it's what we are doing here. I mean, the way there was a town hall and this congressperson was speaking up. I talked 5-7 minutes about it. Many other topics. Here we are talking about it. So, we don't have to try and persuade people. We just have to get the science out, let people read about it, let people discuss it. All we have to do is make it a little more public forum. And there are many other things that the US has going for it.
yeah.
You can say, okay, but exactly where are we going to do this? Now, there's a lot of appropriate land that we don't do anything else with. It's called deserts. And the US has its share of useful deserts.
Right. Yeah.
There's nothing out there, just a lot of hot sand baking in the sun.
Yeah.
Now, one great use of that in the future is solar power. That's ideal for solar power, right?
Yeah.
And one other example is literally this kind of stuff.
Mm-hmm.
It's sand. It's a desert. That automatically means there's no water close by. So you have to be careful, but it's actually a very big benefit that it's extremely dry and no water. A lot of the issues of this kind of things is this hot radioactive stuff is sitting there. How do we make sure it doesn't get out? the easiest way for this, any bad stuff, chemical waste, anything, to get out is water.
I see.
Water seepage, eventually you stick it in a cylinder and you put the cylinder in something, but the cylinders crack and this happens and that happens, and eventually nature finds its way to get water into things like that. And eventually the water may reach groundwater in another 20 years. Water just loves to seep, right? That's what it does.
Yeah.
A desert is a perfect place. You know the history of water flows at various sites. You can study it.
Mm-hmm.
You can trace the fact, what's the frequency of rains, what is the frequency of flash floods, and find a site somewhere in our enormous Southwest.
Mm-hmm.
And these things are very contained. I mean, a typical nuclear core, I don't know, is the size of a room or something. So having 10 of these, over hundreds of square miles of desert, you can easily find the site. And some people will have to live close by and operate, but there are lots of people living in our southwestern states. So people are willing to live all over the place. So once it's operational, the nice thing about this kind of thing as compared to chemical anything is the volumes are way smaller. So, people are now trying to say that coal-fired plants, at least they should have scrubbers installed on them. And so at least all the stuff that the thing is spewing out in the atmosphere can be scrubbed and clean. You can't take the CO2 out. We're talking about how you might take the CO2 out, but that's huge amounts of CO2. The volume here is millions of times smaller.
Mm.
So literally, we are talking of a nuclear power plant that can run for 5-10 years, but the stuff that it's consuming is a room-size object.
Right.
And you can, no matter what you say, it's far easier to control a room-size object.
Right.
The transportation to the site, you have to be extremely careful. But once it sits under the ground, people have said, well, what do you do with it after? The second phase, you shoot the proton beam at it, and after you run it for 15 years or something, and eventually you'll run out because the remaining 25, 30, 40% that you can use is also done. Now what? And the simplest answer is, if it produced the same amount of energy as a typical $50 billion plant does, and suppose it takes a couple of $1 billion to build the accelerator that was running this thing. If you made a right kind of design, you could literally dismantle your accelerator, move it, rebuild the thing somewhere else, and maybe it takes $500 million to move your accelerator. But you just leave the spent stuff right where it is. You don't move it again.
Yeah. I
And
think
so if you have 20, 30, 40 of these, and each one of them runs for 15 years, you're talking of a countable number of places that you could monitor extremely carefully with all kinds of robots and radiation sensors and lots of ways to make sure this thing is sitting there for another 20, 30 years until it becomes non-radioactive. So the containment problem is to be thought through very carefully. But off the top, it sounds like you don't have to ever move it again. Just leave it there, get to another site close by, half a mile away, do it again. And so you can sort of see, do it 5 times every century. And if you have 40 of these things running, and that supplies 30, 40% or some big fraction, and it's controllable. And so you can watch your wind and solar. And whenever you're short of one of those, you pump these things up. I think we should get this info out there and get people thinking, get the critics to express both their emotional feelings and their scientific concerns and engineering concerns.
Right. Right. Yeah. There needs to be skeptics that attack it from the other angle that are scientists. But there's also a huge incentive for our country to do this, because one of the things that is important, of course, in the civilizations of the world in the past is military, but people don't think of the resources they have, and sanctions on other nations and tribes and countries and states, or whatever you want to call it. If we're ever in an energy issue and we don't have, and we have our own, or if the world's in an energy issue, but we have our own thing going on in Arizona with 25 reactors that power this whole country. We don't need to worry about we don't need to worry about China, Russia, anyone that's our enemy, providing, slapping sanctions on us, or stopping us from powering our country. It's our own homebrewed scenario.
Yes.
Another reason why I envision, if we can get the tech there, if we can have private industry meet with your people and you specifically, we can make that case, and then the U.S. would gladly probably throw money at it. I think that's important.
I'll tell you one other thing that I learned about. We talk to colleagues worldwide and so on. It's still true. It was true when I came here 40 years ago. The world, no matter what people say, criticize, and not that everything the US does is great. Everybody makes their share of mistakes as a country, as a people. But still, in the end, there is a big perception out there in the whole world that the US literally is a leadership country. And it's something to be proud of in a way, but it's also a responsibility. People out there watch and they do things, other countries and so on, because the US is thinking about it, because the US has done it. It's being done. Who did it? Well, the Americans did it first. We should get there ourselves. We should not lag behind. They've shown that it's doable.
Yep.
Why can't it be us as well? So lots and lots of things. People, I sort of know in some situations, the Indian technocrats, intelligentsias, for example, they'll always criticize also, but there is also this sense, what's the US up to? What do they think is the next thing to invest in? Which way would work? What would be the solution for this problem, that problem? What's the next frontier? Mm-hmm. We should think about it because they're also thinking about it. How does somebody else know whether it's a bad idea, whether it's going to be worthless? Well, if the US is thinking about it, there's something to it. We should think about it too. Call it technology for the sake of space, or energy generation, or electronics, or software, or name your pick. Many of my colleagues say, for example, China, their political and scientific bodies pay a lot of attention to what is the US investing in. So when this idea, which has been talked about for a long time, we have 300, 400 million people, they have 3 times that.
Right.
They also have energy needs right now, heavily based on coal.
Yeah.
No single country is going to solve the climate issue, because somebody else doesn't solve it, then it's still unsolved. So they are also thinking pretty hard. If you talk to their high-level scientists, they've said, yeah, we've talked about doing this particular type of high-energy physics with a very intense beam. And by the way, our nuclear engineering and our nuclear power folks are thinking pretty hard. It's called accelerator-driven systems. So you basically take this high intensity proton beam, and it will solve the waste problem of the existing reactors, plus it's a source of energy at the same time, and it's controllable and all the other things.
Yeah.
And especially after the Fukushima reactor problem. Chernobyl happened 35 years ago. the tidal wave hitting the Japanese coast and knocking out their reactors there, and the big thing. Another big reminder, look, this is what can happen with that old reactor technology. So the Chinese are also thinking pretty hard. Why don't we think hard about this beam-induced thing? I don't know yet if the Indian community, power base, thinking about the needs of the country,
Right.
their nuclear program may be, I'm speculating here, but it might be more based on breeder reactors and so on, which is
I see.
you take some reactor technology, you extract the spent fuel from it, then you separate out various things and you put some of that stuff back into a new kind of reactor. But again, the same basic principle. It's a lump of stuff. It's got a chain reaction. You control it with absorbing the neutrons or not. You're just swapping out the material in there round and round.
Gotcha.
The beam wave stuff, I'm not sure it's catching on or it's talked about so much in India, but it is certainly being talked about in China.
Gotcha. So the Fukushima one was in 2011. Just want to make
2011, yeah.
Sooner than we thought. So just want to make sure that was there. But the other thing is, so from the people you've talked to, how do you feel? What do you have a time in your lifetime, in my lifetime? When do you think that maybe first world countries, so U.S., we'll say U.S. has all nuclear, or do you think that's even an option? Is it going to be a mix of something else, or are you optimistic?
So let's give it the numbers, because the numbers tell the story.
Yeah.
What has happened, which is sort of amazing. 25 years ago, as a college student, something couldn't have imagined this. We used to all just eat pizza and talk about the dreams of how it would be wonderful, but didn't know anything about whether it's feasible. The amazing thing is both solar power and wind power are yet not cheaper than fossil fuel. Fossil fuel is still cheaper than solar and wind.
Mm-hmm.
But
Right.
the economic cost of solar and wind has steadily dropped for 10, 15 years, so steadily that it is slowly becoming competitive with fossil fuel, which is why solar, which is in some sense is even more risk-free, wind and solar, the infrastructure costs are proportional, right? You build a solar farm over this area, you know exactly, you don't have to put as much money up front and then count on an extremely long thing. It's whatever you build, you get that much out right away. There isn't a minimum scale. If you say you only have enough money to put 10 turbines up, okay, that's a very small scale farm. If you have the money to put 100 turbines up, it's a bigger farm, it will produce more. So that makes it much easier for lots of experimental things to start small and scale up.
Mm-hmm.
With any kind of nuclear thing, there is no small. It has to be this big, a today's technology, $30-40 billion nuclear power plant. So you better be one of those huge, very deep pocket things. But that's a lot of money up front for any corporate board to sign off for anybody else. Mm-hmm. As opposed to, sure, let's build $1 billion solar farm here, see what happens. Okay, let's build a $2 billion wind farm there. Yeah, we can handle that easily. Oh, you want a $40 billion nuclear plant? I got to think very hard about how I'm going to finance this. Mm-hmm. That and the cost reductions of wind and solar, which are keep constantly newer technologies, slowly just pitching a little bit, just cheaper and cheaper. Plus the fact that there is really no fuel, right? The fuel is in the sky and the air. You don't even have to bother with the nuclear, anything.
Yep.
Wind and solar has to be, my guess is 50-60%.
Okay.
It economically, technically, and just simple logic-wise, plus the maintenance. There is a lot of steady state, good jobs You have to think about the people, right? How many people does it employ? It's a good industry for people to be maintaining these things, to be servicing them, to be replacing panels as they run out. If a wind turbine gets stuck, its motor is jammed, this happens, that happens, okay, let's go service it. So when you have large scale things like this, you can have a lot of employment. That's not quite the case, right? With the nuclear, it's a few very high tech type things, and then there's not as many moving parts. So it's a very material and technology oriented industry and less of a people oriented industry. Whereas wind and solar has many other benefits. So employing lots and lots of people, spreading it around.
Yeah.
Imagine earthquake happens, right? If an earthquake happens and it somehow hits a single big nuclear thing, could be an issue. With the new technology, we beam and beaks talked about, it won't have any radiation problem. Hopefully, there's a way to control it. But still, it's knocked out.
Yeah.
Wind, solar is all spread out. Okay, so something happened there.
Right.
1% of the national solar infrastructure got knocked out because of something.
Right.
Okay, we can handle it. Okay, take your nuclear, just increase the power output by a few percent. You can make up for it. Give them 2 years, they'll rebuild it. Okay, we're back in action.
Right.
And there's something beautiful about solar. After all, it's got no moving parts. It's basically processed sand, right? The panel, the solar panels are just sand from which you extract the silicon and you manufacture this thing. And it's covered with glass. So it's sand and glass.
Yeah.
It's kind of
awesome.
Interesting, right? You put it out in a desert. It's just the sand in the desert, just been crunched, and it's now generating energy for you.
Yeah. The problem is the.
So you have to do solar and wind. So we don't need 100% nuclear, was my point. We just need 30% nuclear.
Okay.
And many other things. So US can be a mix like this. Some places out there, imagine Africa, there is a desert there which is as big as the US and China area combined. The Sahara Desert is bigger than the entire continental US, I think.
And China combined? I don't really.
Maybe I'm overstating it. At least bigger than the entire area of the continental US. Let me check the numbers. It's that scale.
Right.
Yeah. US is enormous, right? And now you imagine a desert that big. In fact, I think some UK company is saying, let's go to Morocco, which is sort of not too far from the UK. Find the desert space in Morocco, build a solar plant there, just panels upon panels.
Yeah.
They're trying to figure out how to route all the generated electricity under the Mediterranean, go through the Straits of Gibraltar or something. So it's a small patch of Mediterranean Sea. How to put electricity cables underwater and bring them up again, and then somehow cross the channel and get that power to the UK. So,
not Africa.
So how do you get the power from Western Africa to the UK?
Yeah.
Somewhere through Europe, and some of it has to go underwater. So if somebody can do that, for us to deploy solar power in our own backyard, literally, Arizona, New Mexico, somewhere.
Arizona.
You don't have to do any of this.
Yeah.
So all nuclear, there is one country like this, which is 80% nuclear, which is France. So France is probably thinking, hey, we're 80% nuclear. We can just go nuclear all the way. Why not? I don't know where the remaining 20% is. Maybe they're buying it from somebody else who might be burning coal at the moment, like Germany. But Germans are thinking quite a bit about wind. I don't know. Every country has its plans. So they're talking a lot about the European grid as well and what mix of solar, wind, and nuclear we can do. But and wind has its own huge benefit, which is at least for the night versus day, wind doesn't stop at night, and in some sense, it's even more stable during the night. That's what I heard. So when solar goes away, what do you do? Well, presumably everybody is sleeping, so you don't need as much power if you're smart about it, right? So all the buildings need to have motion activated lighting and stuff, heating, lighting, so that when everybody goes home at night, you're not just heating the building and lighting up the building all
Well,
night.
you can what you can do is figure out how much it. We'll just say a town. We'll call it. There's 1,000 houses in this town, and it has X number of energy that it needs to have. What you do is you build a. We'll call it dark times of the day is 1/3 of the day, so we'll call it 1/3. What you do is you take, in my mind, is you have the output of the daytime in. So you build that many solar panels, and then you build that 1/3 right next to it, and that stores it. It doesn't go directly to the house. It goes underground in a battery or some storage mechanism, and then that kicks on once night happens, because obviously there's no more coming from the main source.
Yeah.
Can do that way.
Yeah.
The big issue with solar, though, is just each individual cell is just not impressive to me. It's not. We're not there yet. I think we need to figure out.
Bad.
No, it's good. I think
we're reaching 25% efficiency. It used to be 5-10%. Now it's 25%. They're talking.
Right. I think it needs to get. What we need to do is understand how plants do photosynthesis. If we can get that on the molecular level,
yeah,
that machine is working. It's over. It's done. We figured out energy, because they are the most efficient energy sources in the planet with how they power themselves with the sun.
Yeah. So photosynthesis is amazing. So
right.
If you read the journals, and people are figuring out what exactly is the mechanism and how the electrons jump from here to there, and what happens to the protons and the hydrogen moving around. And so it's very clever. Yes. So that may kick in at some point.
Yeah. That's
and
the
on the
key.
other hand, the solar industry, the solar panel industry, somebody say we could do this, we could do that. Instead of 25%, we've achieved 26.5%.
Mm-hmm.
Every year goes up by 0.5%, 1%.
Right. Yeah.
If they keep that up in 10 more years, it's at 35%.
Yeah.
Getting somewhere.
Mm-hmm.
The nice thing about solar, of course, is once it's out there, it has very few moving parts.
Right.
So there's almost no maintenance. It's just sitting there passively. All you have to do is simple motors that will turn it so it faces the sun.
Yeah. Yeah.
So everything has its ups and downs. The problem is at night, what do you do? So my colleague and friend, he's a scientist in Congress. By the way, he always makes this point, and maybe this word should get out. Unlike many other countries, especially Europe, our elected representatives are very rarely of a scientific or engineering background. Very rarely, which maybe we could improve upon. Right? He was, for a long time, one of the only two scientists in all of Congress and Senate put together. I think one of them moved on to something else, so now he might be the only one. For a country like the US, which has always been a scientific and engineering leader, so many firsts, right? Who did this first? The US. Who did that first? The US. You think we ought to have not one out of 600, but a little more than that would be nice. So something to think about. So,
I can only imagine what we would be if we had scientists at the helm, or at least 25%.
A few more as part of the conversation.
Yeah.
Help with the facts, how to analyze the facts.
Right.
They don't have to make the decisions, they're societal decisions, but they could just help to get the information to the right people.
Yeah, the problem is a scientist does not make a good politician.
Well,
that's the issue. It's a personality. I mean, could you imagine going to politics? Let me ask you. I don't think you would ever do it, right? So,
I know.
I mean, maybe you would, but a lot of scientists that I talk to, I just have the feeling they would never go into anything near politics. It's just not their personality. So that's the issue.
That's the issue.
But we can do more work to connect the amazing scientific research and things that we do in this country to the leadership of the country.
Yes.
That connection can be built upon.
Yes.
And if it is, we can achieve some amazing things.
Yeah.
Let's go on to your work with the W boson.
Good. Okay. One quick thing in the context of what he said. A little bit of what might be lagging behind, even though batteries have come such a long way, they are still largely looked upon as the solution for vehicles on the road, buses, cars. We have enough lithium and we can build the batteries to make all the transportation. Not an easy task already, but hopefully all transportation can become electric. What is a major fundamental challenge is if you try to do now batteries for general electricity grid backup, like you were saying, charge the batteries at night in a major way from solar, and then run the batteries in reverse, night versus day.
Yeah.
Even that might be possible. It is stretch already, but the real issue is summer versus winter.
Right.
Northern countries, sun is really down in winter. Now you got a serious deficit.
Yeah.
So you're talking such a massive battery farm that you can charge it up over the summer, and then you're withdrawing from it for months and months in the winter. That's a far, far bigger battery. He said, everything is hard, but this is hard times hard times hard. So the solar winter problem to be solved by battery.
Right.
Some of the Northern European countries are thinking, who have hydro. So their great solution, much simpler, is you just run a hydroelectric dam in reverse. So you let the water come down to give you electrical power. And when you have excess solar, you just run it backwards and you fill the dam up.
I call that gravitational energy. I don't call
gravitational energy.
Yeah.
So using the gravitational energy of a dam as a battery backup, way simpler, way cheaper. You already have the dam. You can store water for months.
Yeah.
So the only battery is the gravitational battery for month to month. And every country can't do this, but the ones that do it are thinking that's by far the most fantastic solution. So battery backup is probably not. I would say turning on nuclear power or something at night or winter is probably the ultimate solution, not some enormous. And you have to be careful, right? When you have that much battery storage, if something happens, like you short it or something goes wrong, you'll destroy all your batteries. In that sense, it's a bomb, right? When you have that much energy stored somewhere, your huge battery farm is.
That's
you
true.
light the fuse, it'll go poof.
Yeah, that's true.
So I'm sure somebody's going to think about it and say, let's not do battery backup for large scale things. Little things is okay. Okay, now let's talk about my science.
Yeah, so let's dive into it. I love when you intro particle physics before you talk about. I think we should do that before we talk about the W boson. So maybe you can just kind of brief history for the audience of particle physics and how we got to this point, and then what the Higgs, and then we can get to the Higgs field and the good stuff.
Okay.
From there.
So let's do a few minutes of soul searching from the late 1800s.
Yeah.
Late 1800s, people thought we have now a theory of electricity and magnetism, making radio waves, all understood. And they had Newton's laws of motion, so they could build buildings. An Eiffel Tower, mostly air, but just a few steel girders strung together the right way. My God, this thing stands forever. Everything understood. A few cracks developed. People discovered radioactivity, couldn't understand it at all. Radioactive elements, radium, something. Somebody wraps it up in a photographic plate or something. Next day, the plate looks all darkened. So there's no light here. How can it feel exposed? So lots and lots of things started happening as radioactive was getting discovered. Now, Other puzzles happened. People said there's something odd with the old laws of physics. It doesn't quite work here. It doesn't quite work there. People were thinking quantum. What is this funny quantum business? Then I guess the beginning of particle physics as we know it would be 1911. So a couple of students of Ernest Rutherford at Manchester, a fantastic scientist, and he was telling them, try this, try this. They took a radiation source. They didn't know what radiation it was at the time, some high particles coming out of stuff, radioactive stuff. They exposed a gold foil, thin foil of gold, throw the radiation through it. Their understanding of the atom was that it's a mix of electron, positive charge and negative charge, like a plum pudding. They would call it the plum pudding model. So you just mix it all up and you look at a plum pudding, you see plums here and there, you see the bread, you see the dough, and it's all mixed up. So by that time, from chemistry and so on, they knew there were positive and negative charges. Lots of electricity experiments had been done, and they knew stuff had positive and negative. You could separate it out, and you could let them recombine, and they attracted each other. The theory of atoms had come along. Chemists were counting, when you burn this stuff, then it looks like it's always an X amount of this and Y amount of that combined to get Z amount of this. And the ratios of X, Y, Z were always the same. So they were writing down chemical reactions. So it started to look like when hydrogen and oxygen burn to form water, it's never some random proportion. It's always a 2-to-1 thing. It's 2 of hydrogen, 1 of oxygen makes water. So the logic had developed by that time, the atomic theory, that this would make perfect sense if everything had some smallest unit, which they called atom. And so a water molecule would be 2 atoms of hydrogen, 1 atom of oxygen. If somehow they stuck together, you get a water molecule. Now you just multiply that by as many molecules as you want. So this indivisible property logic was developed. They had studied properties of gases by then, and they thought, if the molecules really were little things and they were just bouncing around like that, you could understand how a gas behaves. The gas is just a cloud of these molecules bouncing around. A liquid, when these things come close together and stick, then it becomes a liquid. If they stop moving around, it becomes a solid. So they had a theory. So I would say in that sense, particle physics, if you think of it as what's the smallest unit that explains how stuff behaves, it's all about the properties of the smallest piece, and then you just multiply it by as many as you like. It's the little things that interact that make the big things. And if you want to understand the property of the big thing, look at the property of the little things, how they act with each other. That's what we call the reductionist logic. Try to go small and small until you get to the smallest thing. You figure that out, you'll understand how it all works. That reductionist approach, I would say, is particle physics. That's what particles are. They are the smallest thing that make up everything else.
And that's where we get to the smallest point where we're not even seeing anything anymore. We're actually like diving into what it does when we scatter experiments and like almost how it interacts with things.
Yes.
We talked about, but
so smallest means, as far as you know, it's not made up of anything else.
Right, exactly. Quarks, all that stuff.
Quarks. So back then they didn't know. They didn't even know about protons back then. But they knew atoms were the smallest element things and molecules were the smallest things about any substance. And molecules are made up of atoms sticking together. All logically makes sense. So they said, well, then what's an atom like? So this is the next phase of particle physics, 1890s. Oh, well, what do we know? There's positive and negative, so an atom must have positive and negative. Let's mix it all up, and that's your model of the atom. It's like a plum pudding with positives and negatives in equal amounts mushed together. So that was the state of particle physics until then, in a sense. So now comes Rutherford's experiment, and what they found was most of the time the radiation would go right through, and every once in a while it would bounce back. So they had a way of observing these radioactive particles, which is basically like a TV screen. So they knew how to make glass or screens like this, and you would coat it with the right kind of material, and you would just go to a dark room, and every time a radioactive particle hit this chemical, it would emit a little bit of light, just like a TV screen used to do. Right? Now we have flat panel screens, so they don't work that way, but the old big TVs, they worked exactly like that. So they said, how could stuff be bouncing back? Because if you throw something through a plum pudding, it just goes through some mushy stuff and it just goes straight through. There's nothing in there to bounce anything back. And everybody knew basic mechanics. If you want to bounce something off, you can't be mushy. You need to be hard, you need to be heavy, you need to be like a brick wall or a solid steel thing so that you can, ricochet a bullet of something. You would say, if you shoot a bullet at something and it bounces back at you, it can't be mushy stuff, right? It's got to be hard and heavy and tough. So they said this plum pudding model of the atom is out of the window. The atom has to look extremely different. It's got to have a heavy, big, small core. Okay, the core could be positive or negative, so let's say it's positive. So then where is the negative part going? Well, the negative part has to be outside. So now the electrons are on the outside and the protons are on the inside. And this structure would simply not follow the known rules of physics. What his experiment was showing as the structure of the atom was violating all the rules of physics they knew at the time. That one experiment. The electrons should not continuously circle around. They should eventually radiate all their energy as radio waves and fall inside the proton. But they weren't. So this became the beginning of the quantum theory of small things. So now they really knew electrons, protons are not following Newton's laws. They're not following rules of electricity and magnetism as they knew at the time. There's something more going on. A completely new principle is at work down there. And this is how they started understanding that you got to have this entire principle of quantum mechanics, which doesn't think of particles as particles. In a word, think of everything down there as being made up of waves. It's all waves. An electron is a wave, a proton is a wave, a quark is a wave, everything is a wave. So the way you think of an electron going around the atom is that it's not going around the atom. It's like a wave which is anchored in place like a violin string, tied down at both ends.
Probabilities.
It's a probability. So the wave describes the probability of the electron. So it's not like something is going up and down. It's like there is a quantity that goes from 0 to up and then down again. And what is that quantity? It describes the probability.
Now I have a question. I have a question off this.
That's
is where
how quantum mechanics has to be thought about. And such a wave can sit around the proton standing there. It's called a standing wave, just like a violin string, going nowhere, but just oscillating in place.
Yeah.
The electron is like a cloud, but in the shape of a wave with a probability that's changing here and there, but it's a standing wave pattern. And a standing wave doesn't have to go anywhere. It just sits there, sort of oscillating forever. And that rescued the whole picture, how the atom is actually stable.
Yeah.
Completely new paradigm. Go ahead.
No, so yeah, so my question is how, so I'm not satisfied with the probability because I know it's the best we can do, but how close can we get to the real because in reality, it's not a probability. The probability is, of course, unless I'm wrong, the probability is the best we can do with our measurements. We have to slap a probability in that formula. But in reality, there is something set in stone. Nature doesn't have probabilities, right? Unless, so am I wrong or am I right? Or am I in the middle here?
You are probably raising, in quantum mechanics, this is probably the question of the century. Right. More than 100 years have gone since this quantum principle has been laid out. The math has become extremely rigorous. I don't know how many geniuses and very, very, very smart people, all levels of smart people have done quantum calculations on all kinds of things for 100 years. Many of them puzzle on this question. We are calculating with this rule of probability, and every quantum experiment we've ever done, bizarre or not, gives the right answer. So nature, we are becoming almost philosophical, because now you have to ask, well, when I observe nature, what do I mean? Who am I? Am I my eyes? Am I my brain? What am I? So the whole definition of observer, observing some other thing, is itself up for grabs. What does any of this mean in a mathematical description? And you can name the 20, 30, 40, 100 smartest physicists of the century, and they have thought about this question. And people keep wondering, is quantum, the way we write it down, an intermediate step of our understanding to something deeper? And there are these ideas, and I'm no expert at this, but I've heard things like hidden variable theory, that there is something underlying that we don't observe, but from that perspective, it's not probabilistic. But you only see some aspects of it, and the rest remains hidden.
Right.
In the hidden thing, it's not probabilistic, but because you observe only some aspects, to you it seems probabilistic.
Yeah.
People find this sometimes an appealing way out of this puzzling quantum paradigm, but others will say, you've just replaced one bizarre thing with another. Okay,
Right.
you eliminated the probability aspect of it. That sounds great. On the other hand, you've invented another bizarre thing, which is hidden. What does that mean, hidden? How can some things be observable and the rest is hidden? How does nature decide what to hide and what not to hide?
The rule
Well,
of science is we can't have any. The rule of science is we can't have anything hidden. That's the whole. Yeah, we have to measure it. But what I'm getting at is, I think the thing that we can't measure is having a symptom in our world, and that symptom is the Higgs field.
So for the time being, I know that there are many, many, many smart people who literally think about the theory of quantum. Is there a deeper theory which explains quantum? In the same sense that the atom is now explained by quantum, does something explain quantum itself? There are enormous puzzles, philosophical almost, because it leads to thinking. I mean, everybody from Einstein down has thought about, really? Is this the way nature does things? That the best description you can do is a probabilistic description, and it works amazingly, and nobody has ever found a problem in the calculations of quantum. But just conceptually, it seems, really? This is the way it works? Well, so we are there, and if you can answer this question, you'll become the best known scientist of the century. I guarantee you. Not this year or next year, the century, if you can explain quantum. And prove it, find some experimental way of actually saying that's the way quantum works in a better way. It's 1,000 times beyond me in answering, but it's the question of the century, literally, in some sense. Having said that, what particle physics is doing for 70 or 80 years now, through works of many geniuses, including Paul Dirac in 1932 and so forth, he started combining the rules of special relativity, Einstein's special relativity theory, which is a theory of space and time, with these other funny rules of quantum. So you get a quantum and relativity theory. This is called quantum field theory. So our existing description of Higgs, electricity, magnetism, quarks, electrons, everything, the strong force, the weak force, the W boson, all of them are quantum fields. They're all something that particular quantum field, the W boson field or the Higgs field or whichever field. There are n different kinds of quantum fields. Each one of them follows the rule of quantum mechanics, follows the rules of special relativity. And ultimately, what you calculate for that quantity is the probability of the object. So I'm
for
going
the
to
audience, can you try to define field real quick?
Let's think of a wave. I think you've all seen a field. You go stand on the beach and you observe a wave coming towards you constantly, right? You say, what exactly is that wave? What's my description of it? Say, it's water going up and down. Is the water coming towards me? No. The water stays in the ocean. You're over here. The water's over there. It's not moving towards you. But it looks like the wave is moving towards you. So what do I mean by that? What is really happening is the water has a pattern. There is a height to the water everywhere. Let's call it y. So y for every position. So horizontally, let's call that distance x. The height of the water above the level of the ocean, we'll call it y. So in mathematics, you'll call that y as a function of x. You tell me any position on the water surface, I'll tell you the height of the water there. So it goes up and down and up and down and up and down. If you look at that pattern, wavy pattern, sometime later, it's shifted. So all of the crests of the waves have moved closer to you. All the troughs have moved closer to you. So this y as a function of x, every second is a little different. So I say, okay, it's a moving pattern. How do I describe that? I'm going to say it's not just y as a function of x, but it's y as a function of x and time. Now you have to give me an x position and a particular instant of time. I'll tell you what's the height of the water. As time runs along, the pattern is moving. So the wave pattern approaching you is not that the water is coming closer to you. It's the height of the wave follows a particular pattern as a function of position and time. And when you watch that pattern, it seems like the pattern is moving towards you. All that the water is doing is supporting that pattern. It's saying the pattern is a description of the height of the water. Yeah. This is what we would call a field. The surface of the water is acting like a field. What is it? It's just the surface of the water. What's the field? The field is the particular pattern that surface is following. And that pattern, so if you keep asking me, what is the pattern? Well, it's just the height of the water is what I'm describing. Now you turn this into your quantum field and you say, what is that? It's also a pattern. It's y as a function of x and time, just like the water surface. You say, okay, good. Yeah, I understood you were describing the water surface before. I can see it. I understand water surface. I can see ripples. Yeah, got it. What are you describing now with this quantum field y as a function of x and time? I'm going to say I'm also describing a pattern. So you keep asking me, pattern of what? What is there to describe the pattern in or of? There's no water there. What is there? And I'm going to say this pattern is the pattern of the probability of the particle being there. So now you say, well, what's a particle?
Right.
It's the thing whose probability I am describing. And you say, well, what is probability? And that's probably another question of the century. What is probability? Once we get to the situation that you ask what is probability, it just means if you could make a particular observation over and over again, 1,000,000 times, a gazillion times, then the number of times you will get this answer, and the number of times you'll get that answer, and the number of times you'll get that answer. The fraction, if you add up all the answers, you'll always get an answer. So the probability is 1 to get an answer. But how often do you get this answer versus that answer versus that? So that's the ratio. So that's the meaning of probability. So that means if you look for this particle here, how often will you find it there? If you look for the particle here, how often will you find it there? If you only look once, it's going to be one of those, but you haven't followed the probability logic. You have to do it a gazillion times, and then you count how often, how often, how often. That's what you mean by probability. And this wave, this quantum field theory function that I wrote for you, if you compute that thing and then you do your gazillion measurements and you compare, does this tell you exactly how often this will happen versus that will happen versus that will happen? You'll get the right answer. Do you find that a satisfactory description of this particle's behavior? In the probabilistic sense, yes. Can we do better than that? To our knowledge, no. Now you can complain, this is bizarre, but there's no point in complaining about nature, right? It is what it is. It was here first. The same electrons that we are struggling to understand are in our brains right now and in our bodies, and I can eat and drink and talk to you because of the electrons following the rules of quantum mechanics. So for all we know, that's the way we work.
That was perfect. Yeah.
This field is a space and time dependent function which has a probabilistic interpretation as opposed to the height of the water or something like that. Sound waves. What is a sound wave? You say, ask my ear. I hear a wave. It's high pressure air and low pressure air, and then high pressure air and low pressure air. So when I speak, the membrane is oscillating back and forth and it's pushing air towards the microphone. So as it goes back and forth, it's creating high pressure air and low pressure air. So there the wave is, the field is the description of pressure. Over here it's high pressure, then it's low pressure, high pressure. So you ask me where the pressure is at any point, what value, here, at which time, I can tell you what the pressure is. It's a function. That's a field. So any function that changes continuously as a function of space and time and has a bunch of other mathematical properties is the definition of a field. And it seems this math actually describes the probabilities of whatever we call particles. The smallest indivisible element unit of electric charge or whatever that thing is, it's got a probability description of being here, there as a function of time. And that whole description is called a field. It gives you answers because it's mathematical. You can calculate it, gives you answers, you can go measure it. Lo and behold, right answer. You can't sneeze at that, right? No matter how bizarre it sounds.
Right. Yeah.
And not only do you get the right answer for something that's already happened, you can get the right answer for something that's going to happen even before you do the experiment. And then you can go do the experiment and check it against the math that you already wrote down. And that's called a prediction. So if you say, throw 2 electrons at each other and tell me how the 2 electrons will repel and where will they end up. Well, I'm going to tell you it's got a probabilistic description. They might end up here, they might end up there, they might end up here. But I can tell you the probabilities of them ending up here versus there versus there. Fine, you wrote it all down. Now you go throw electrons at each other over and over again. Watch where they come out. Measure the probabilities just by counting the number of times. Check against the math you had done. Right answer. This is particle physics. So now we found what the electrons, then we found more objects like the electrons.
Yep.
We don't know why there are multiple types, but that's an unsolved mystery, but they're out there. People discover these things, amazing Nobel Prize winning things. Then people said, is a proton really a point object? They started shooting electrons at protons in the 60s and turned out, hey, the proton breaks up. Since it breaks up, it cannot be the fundamental thing. There must be stuff inside. You can blow it apart. You cannot blow up an electron. They've tried to blow up electrons. They don't blow up. So that's what is telling us so far the electrons are, there's nothing inside an electron. It's the smallest it gets. But a proton is not the smallest it gets. You can break apart a proton and it's got quarks inside, and it's got gluons inside, and it's got W bosons and Higgs eventually. So the picture has filled up. We've got 6 types of quarks. The lightest 2 are so-called the up and the down, very simple names. The proton and the neutron in the atom are made up of combinations of up and down. You mix them up this way, you get a proton. You mix them up the other way, you get a neutron. You can now start mixing up the 3rd way and the 4th way and the 100th way, and you start getting new objects, new particles. And we found hundreds of them, but all of them are built out of these building blocks. So the particle physics logic is working. Just like molecules are made up of atomic building blocks, now this entire zoo of other things is built out of ups and down quarks, just mixed up in different ways. And they seem to be following the rules of how the up quark behaves and how the down quark behaves. So you write down the rules and you say, according to the rules, just like I can do chemistry, by the rules of oxygen and hydrogen, I can hook it up like this, I can hook it up like this. I can get all these different kinds of molecules. All the different ways you can hook up the quarks is actually producing all the other objects that ought to exist. So far it's all working out. The heavy quarks, because they have more energy, they can radiate away W bosons and Higgs and whatnot, and eventually land up as the lightest quarks. Oops. So all heavy fundamental objects are not breaking up, but they are throwing off these other particles and decaying to the lighter ones. So that's why when we look out in nature, you just see the few lightest ones. You just see the electrons and the up quarks and the down quarks, and all the heavy particles, even though they're fundamental, they've radiated away their energy and decayed to the smallest. So that's why you have to reverse that process. You have to throw high energy electrons or protons at each other, then the decay process gets reversed and they go up in energy and the heavy objects get made. So the Higgs boson and the W boson and the top quark, they get created by just reversing the process that happens in nature the other way. So at the time of the Big Bang, the energy was sufficiently high that all the heavy particles were also produced. They were all the top quarks, Higgs boson, they were all just flying around like a gas. But as the universe got bigger and bigger, it cooled down, the energies got lower, and so these high energy collisions weren't possible anymore. So then only the lightest particles survive. And that's why, when we look around, we only see the electrons and the up quark and the down quark inside the protons and neutrons. But the other ones are part of nature. They just, by the natural decay process, have come down to the lower energy ones. So you can reverse that and see, if I really want to see what nature can do, I can make these things.
So at T0, everything was at its highest energy.
So we believe. I mean, nobody was there back then, right? So.
Oh, I thought someone was there. No one was there. Yeah.
So exactly, it's like history. If you tell me that I have figured out what human beings were doing 20,000 years ago, somewhere in the Alps or somewhere in Africa, you say, how do you know this? You weren't really there, right? They didn't write it down back then, 2 million years ago, 1 million years ago, human beings weren't writing. How do you know? Look at the clues. I can see their footprints sometimes, the fossils, the impressions of this, that, the bones I can find.
Right.
If you apply the rules that we know today and just say the same rules were working, physics hasn't changed.
Yeah.
So these bones in this pattern have to mean they were this height and this heavy and they were walking like this, and I can see the instruments and they were hunting like this. It's a recreation from the remains and the clues that you find now. Yeah. What we are doing is we're observing the universe now. We are applying the rules of quantum, special relativity, general relativity, Einstein's theory, all the theories that we've checked out. If you apply those theories to what the universe looks like today and do the math, you get what must have happened 1 billion years ago, what must have happened 10 billion years ago. Then you say, if that must have happened 13 billion years ago, I should be able to see another clue if I look over there. And then you say, look, it's happening exactly like our math is telling us. It's making sense. It's adding up. And that's the best we can do, right? Whenever existing clues fit together with your math, with your theory, and you make a calculation and it describes the next thing you see and the next thing you see, and you keep looking, and this is what we do in Snowmass. You say, if this theory is right, I should be able to look at that thing over there and I should be able to see that. So let somebody says, okay, what would it take? A big telescope, what would it cost? Sounds like a very important thing. Let's go build it, let's go measure it. And if you see exactly that, you say, hey, what we thought we understood is actually right. That's science. And sometimes you get a surprise. You see something in an experiment which is not what your math was telling you. And the first thing you say is, let's repeat the experiment. Maybe we screwed up in observing. Then you repeat the experiment, somebody else goes and does it. No, same answer, same answer. Now you say there's something wrong in my math. My theory is flawed. It doesn't have the right explanation after all. Maybe it's 98% correct, but it's got a 2% problem. What would be the right theory that would explain it? This, in a sense, this is where the W mass is at.
Yep.
This whole quantum picture of the electrons and the quarks, how exactly do they interact with each other? The math is now so advanced that we can actually calculate exactly the property, every property of everything, almost, not everything, but almost everything. So this is where the personal part comes in. Why did I choose this particular thing to measure for most of my life, 27 years? Is I anticipated, people helped, that the mass of the W boson is a quantity that ultimately the math will be able to calculate exactly. So if the math is right, we should get this number from the data. And so now I got a reason to go measure it with extreme accuracy. Either I get that number, that means great, our 100-year-old math is still accurate. Well, that's a great achievement. But if I get a different answer, in some sense, for a scientist, that's even more exciting. Because it means, hey, this math is working so well, it gets this right, it gets this right, it gets this right. Why would it not get the W mass right? Why is what I'm observing different from what the math says it should be? Maybe we are missing something in nature after all. Maybe there's a small piece that needs to be added. Maybe the theory has to be expanded. Maybe there's some principle at work that didn't show up anywhere else, but it shows up here for the first time.
So what are you seeing? I need to know. I need to know what you're seeing, and Are you excited about anything?
I think it's super exciting. So exciting is not a strong enough word. I shouldn't. You want me to speculate?
Yes.
Yes, you want me to speculate. So there are analogs of this. So I'm thinking of examples which sort of illustrate how similar discrepancies in the past have meant something big. What we didn't know before, we suddenly know now. What are the possibilities? So I'll go back to the late I forget the 1600, 1700. I should look this up. People were observing planets. So at some point, people had measured, and they knew there was a planet called Uranus. So they knew its orbit goes around how many. And they were looking at how exactly it moved through the sky. They were calculating Newton's law of gravity. They had all the other planets they knew from the Earth and everything, sun's gravity, the gravity of Jupiter, the gravity of Saturn. And back then, I mean, it's impressive how people were calculating by hand. They were calculating literally by hand the gravitational force of all the other planets on Uranus as everything moved around, and said, I can tell how Uranus should be moving. Every day it should move like this, like this, like this. And somebody started saying, but look at the data. It's actually not moving that way. It seems to have a weird kind of motion. Sometimes it does something funny and moves in a bizarre way. It doesn't agree with the calculations of Newton's gravity with all the other planets. So, wow, amazing. Could this finally mean that actually Newton's law of gravity is slightly wrong?
Oh, it's William Herschel, I believe, right?
I'm trying to remember the names. Could be. We can check this. You can Google it in 2 minutes. Okay. But so that was one option. But somebody said, no, hold on. There's a simpler way out. We know of all the planets closer to the sun than Uranus. You've calculated the gravitational effect of all of those on Uranus. What if there's another planet further away from Uranus? So the solar system doesn't stop at Uranus. There's another planet out there. So if I take that hypothesis, let me put some hypothetical planet out there, redo the calculations over and over again until I get the right answer. What do we mean by right answer? Until I get the answer that I actually see. If I turn this logic upside down, I am saying, therefore, there's another planet out there. Nobody knows there's a planet out there, but I'm telling you, there's a planet out there. It's also exerting a gravitational force on Uranus, and I can do my calculations so carefully, I can actually tell you where that planet is.
And we know it's not a star because if it was a star, it'd be way far. It wouldn't be exerting any energy on Uranus. So they knew it would be a planet. So they can do it.
It has to be somewhere close enough
Yeah.
that its gravitational effect on Uranus is actually causing Uranus to be perturbed. Right?
Because at that point, it does look like a blip, like a star, but it wouldn't be a star. It would be a planet.
It would be a planet. So the prediction was so precise, and some people say, blah, this, that, or the other. And some astronomers said, okay, I'll take your word for it. Literally, I think we can check this history from the right sources. But they literally went and made the observations at night with the telescope or something they had, and basically immediately confirmed this calculation was right. They do see something like a planet exactly where the calculation said it would be. And that was one of the biggest triumphs of the whole scientific method, right? The fact that you have a logic, that it's mathematical, it's debatable, multiple people can do the math, multiple people can check each other's math, see if they're getting the same answer, look for silly mistakes in the math, whatever. And the math they're doing is based on a universal law of gravity, Newton's theory of gravity, and the fact that it fits all the other things that you know, and it even makes a prediction for something you didn't know, and lo and behold, even that comes out right. I mean, the fact that you could think and put logics together which are exact, not just word logics, right? Not just debatable things, but mathematical calculations, and explain something in nature. Think of the times back then, so much dogma, so much, beliefs and this and that. And here it is kind of independent of humans. There's a way of thinking and doing things which is empirical, factual, mathematical. It's not about opinions anymore. It's really, we can all see the logic working. You can go and check that the planet is really there, right? Don't use my telescope. If you don't trust my telescope, go check with your telescope.
Right.
You don't. Maybe I got fooled by some clouds. Okay, you can go to a different location and check it there. So every question you can ask is logically checkable.
Mm-hmm.
It does something much more than science, right? It somehow puts our way of thinking and living in a certain perspective,
right?
Which is beyond just individual things. We are all somewhere part of a grand scheme, which is democratic in a sense. It doesn't give any one person more power than anybody else. Nobody is more important, less important.
No.
So now fast forward, there are many things in particle physics which got measured this way and that way. What it could mean in a corresponding sense here is, what exactly does the mass of the W boson come from? So in our standard model theory, particle physics theory, the whole property of mass is now understood to be not fundamental. So in all, Newton's laws you learn in high school, Newton's laws, you say M equals force divided by acceleration. So you apply a certain force, you get a certain acceleration. That means that object has a certain mass. Nobody explains mass in Newtonian rules. It just is. You just take it for granted. It turns out we've been calculating these laws of particle physics, quantum theory, 50, 60 years, and it started getting noticed back then that to make a correct mathematical theory of forces and electron and so on from all the other properties you had observed, those rules would be badly violated if the W boson or the electron or the quarks had some intrinsic mass. Then the rules fall apart.
The standard model.
Yes.
Right.
So they had to invent a logic by which everything starts out massless. So it's a very bizarre thing to think about what a massless thing is, because everything around us is massive and sits in place. It's got inertia, it's got mass.
Well, energy doesn't need mass.
No.
Have you thought of that with your respect to the W boson and how it can maybe be compensating with energy for the crazy measurements?
If you think of how Einstein explains mass and how particle physics explains mass, the logic of mass is energy is fundamental. There are all kinds of energies. It takes this form, that form, that form. But the one thing that unites them is they're all different kinds of energy. The simplest kind of energy now, the way we look at it now, is kinetic energy, the energy of motion. And in a very fundamental sense, the truly fundamental form of energy is only kinetic. Everything is, by its very nature, by the basic equations of quantum and special relativity and everything else, everything is automatically moving. That's the basic state of any quantum field is that it moves. So it has kinetic energy, and that's all it has. What the mass mechanism is doing, and this is where the Higgs mechanism kicked in and why it was therefore so important that we find it, or something that does that job, is the idea of the Higgs mechanism is to convert the kinetic energy of motion of every particle, the W boson, the electron, whatever, into another kind of energy which doesn't move. Now, we are so used to energy without motion, which is, if I look at this cup, it doesn't have any motion, but does it have energy? Yes, it's got mass, and E equals mc squared. So the mass itself is a kind of energy. Originally, nothing has the mass type of energy, is the logic. The Higgs is able to convert the kinetic energy of motion into another form of motion of energy which is static. So kinetic energy is energy of motion. You somehow have to take the motion away and yet leave the energy where it is. What? Now, you look at the math of the Higgs mechanism and all of this, and it's, I see, this is how it works. And we can sort of understand it, how exactly it's going on. There are analogies that we can help understand it. Effectively, it takes the motion away, but energy is still conserved, so the energy doesn't go away. When you do this, you say, well, if the motion is gone, what's the energy going to look like now? It doesn't look like energy of motion. What does it look like? It looks like mass. And now you do the math of everywhere that we had put mass before. How was the mass showing up in this equation? How was it showing up in that equation? Oh, it always was a kind of energy that sits in its place and doesn't move. So now the whole thing comes together. Wherever we had sort of invented this notion of mass, this logic with the Higgs field and everything now explains it. That's what mass was all along. It was the energy of motion that was present initially. Then this Higgs thing does its job, and it takes the motion away, but leaves the energy where it is. And from that point on, the equations look like the equations of mass. And that's how the electron gets the mass and the W boson gets the mass and so on. So this is your basic calculation of what the mass of the W boson would have been. So now you can put the logic together and say, okay, now I can calculate what the mass is. So if you don't measure, now comes back to my measurement. If you don't measure the same value as this Higgs logic is telling you, you sort of are forced to say, maybe in nature, the Higgs mechanism is not the only thing going around. That seems to explain 99.9%
right
of the mass of the W boson. So it's almost there.
And you've done this, many times with many magnitudes of order of magnitude of correctiveness, and so you're sure that this is off. This should be something, and it's not. Pretty much, right? It's not a question to you. It's just I'm letting the audience know that it's real. It's there, like tangibly. There's something off. That
yes, I am sure. We discussed all the techniques, like you said, all the things you have to do to make this observation. Techniques developed literally 2.5 decades. To a certain extent, the single thing I've been doing for my entire research career, I've done many things in parallel, but this is the one thing that never went away. Other things I did for 5 years, and then I did something else, then I did something else, and something else. But the one thing I never stopped doing in parallel all 27 years is constantly develop better techniques to make this one measurement. And the better the technique is and the more data you get, you combine those two things together, you make your measurement more accurate. and
So
more
what's the
accurate,
delta?
more
What's that?
accurate. Sorry, go ahead.
No, I was just gonna say what's the delta? How do we explain this? What use your intuition after 27 years? Like, what do you think?
So let's take the analogy of the Uranus motion. All the other planets, along with your gravity theory of Newton at the time, says the orbit of Uranus is almost right. There's just some important but little piece that's making a tiny difference to it. Turns out to be another planet, right? Pretty big deal. Neptune is out there. Nobody knew there was a solar system went further. So what my interpretation of this deviation is certainly in nature, there is the Higgs mechanism. There's plenty of other evidence. Not only is the Higgs boson itself found, which is the single biggest evidence, but all the properties of the Higgs are being checked. Other measurements are being made with the LHC for the Higgs for 10 years now, getting more and more accurate. And the Higgs mechanism is here to stay. It's doing 99.9% of the job to describe the mass of the W boson. The thing that should have been zero is this massive number. 99.9% of the number is explained by the Higgs mechanism. So, fantastic. But the remaining 0.1% is telling us there's something else going on as well. There's more to the story than just the Higgs. The Higgs doesn't complete the story. So in the standard model, the existing theory, which is the nature of science, you never randomly make your theory bigger and bigger. You always keep the minimal theory that works. So if the Higgs was explaining everything, you would say all we know is described by the Higgs mechanism and all the other stuff. It's like saying the orbit of Uranus is exactly explained by the remaining planets and the sun, and there's nothing else. The little part that I'm saying is additionally there means in addition to the Higgs, there's something more. Now, why is that a big deal? Because the Higgs itself took us 50 years to figure out. Took us 50 years to find that mechanism. I'm saying 10 years after that, there's more to it than that. So what could be the more? Here, I'll borrow ideas from my theory friends who think about these things, right? My investment is all in the measurement of the quantity. Then there are so many colleagues worldwide who have now written 180 papers in 4 or 5 months. So we came out in April. So May, June, July, August, September, almost 5 months. In 5 months, there are almost 200 papers which are explaining what the additional part could be. A lot of people have a lot of ideas.
Okay.
The essence of the ideas is sort of falls into a few categories. So I don't do those calculations myself, but I've understood at some level what the essence of the ideas are. What could be the additional part that's making the 0.1% difference? Simplest idea out there, I would say, is we are at the moment saying the Higgs one Higgs out there and that does the job. The simplest extension of that idea is the Higgs is not alone. Imagine the theory being expanded just a little bit, adding a second Higgs. Could the whole mechanism be done by 2 Higgs together, like a partnership is going on? One of them does most of it, the other one does. Could that calculation modify the answer for the W mass? Turns out yes.
So we'll have to call it the Kotwal mechanism, right next to the Higgs.
Let's be modest.
No, we're gonna do it. We're gonna figure it out.
Yeah. So I'll stick to the scientific logic, right? You can say as what you like.
Right,
It's called an extended Higgs mechanism.
Okay.
A couple of Higgs are doing it in partnership. Then you can start saying, is the second Higgs just like the first one? The answer is no. It could be.
No, it can't be.
It could have a property which is extremely interesting because now I'll talk about dark matter. So that's my favorite idea.
Right. Yeah.
We know there is dark matter 4 times as much as matter. The only thing we know about it is that it exerts a gravitational force. So when you look at the motion of the stars, it's like the Uranus-Neptune story all over again. You look at all the stars, you look at all the stuff you can see, and you calculate the gravitational force, and that tells you how fast things should be moving. And you look at the galaxies and everything, and you find they're moving faster. So that means there is more force out there than the mass that generates it. So where is the extra force coming from? It's the dark matter. So this is the first evidence, but there are lots and lots of evidence now. And every time you do the math, you find the motion of the galaxies and the formation of the galaxies, and I'm not even saying all the other evidence. It all fits together if the mass of all the stuff that's out there in the universe is only 15% protons and electrons and neutrons, 84 to 85% invisible stuff. And people have said all kinds of things about invisible stuff. What about stars, which are so dull, they're not producing enough light that you can't see them? So they went out and checked this logic, and they checked the logic for black holes, and they checked many other things. It just keeps looking like, no, there's some particles that are invisible, just floating around in the universe and around the galaxies. Yeah. So we think there are invisible particles. So what does it mean, invisible particles? It means that they don't experience the forces that we know. So they don't have the electric force, they don't have this force, they don't have that force, they don't have the force.
Invisible in this context means unmeasurable to our certain technologies so far, pretty much.
Unmeasurable with the forces
of the standard model.
Yeah. But detectable with the one other force that we've known forever, which is gravity. So every which way, when you look for the gravitational effect of dark matter, you find it. So they do exert gravitational force. That's how we know they're there. But they don't exert apparently any other force. Is that what? How can something not have standard model force?
Yeah.
Actually, it's not that bizarre because there are 3 forces in the standard model. There's the one felt by the quarks inside the proton, that's called a strong force. So that's mediated by things called gluons, or funny names.
Yeah.
Then there is the weak force mediated by the W.
Yeah.
Then there is the third force mediated by the electric charge. So electricity and magnetism, that's the third force. Is it possible that something experiences none of these 3 forces? Sounds bizarre until you look and say, does every particle that we know about experience all of them? Yeah. The quark experience all 3. So they're participating in all the 3 forces of the standard model: the strong force, weak force, electric force. If you look at the electron, it experiences 2. All right. So 3 is less than 2 is less than 3. That's still 2 more than 0. Yeah. Then you ask for the neutrinos. So these are the very funny ones, very difficult to detect. And why are they so difficult to detect? Oh, because they experience only 1.
Yeah, supernova.
So when supernova goes off, then you produce so many neutrinos because the weak force is active in there. So the universe is filled with these neutrinos, but they're whizzing around so easily. Why? Because we only experience the weak force, and you hear the word, it's a weak force, so hard to see. So when the neutrino was postulated, 1937 or something like this, people said, this is nuts. How can you postulate a particle which is unobservable? People said, but it's got the weak force. But people then calculated and said, the weak force? It's so weak, we're never going to see the neutrino. It's so weak, we'll never see it. Give 20 years and a bunch of smart people, a bunch of smart ideas, and they say, hey, a nuclear reactor is kind of like a supernova. It's doing a lot of nuclear reactions, and they involve the weak force. So the nuclear reactor is actually spewing out gazillions of neutrinos all the time. What if we put a detector like 20 feet away from a reactor and just wait a few years and have incredibly sensitive detectors? Maybe we'll observe a few neutrinos once in a while. Lo and behold, they got a Nobel Prize for seeing the invisible particle. So what people say is impossible, somebody figures out within 20 years.
Yep.
And now we've got gazillions of neutrinos flying around and we're detecting them all the time. So
Yep.
never say never, right?
Right.
But here is the evidence that there are particles that experience 3 of 3 in the standard model forces, 2 out of 3 in the standard model, 1 out of 3 in the standard model. Why is it so bizarre that something else could be out there that's 0? It just could mean that there are other forces in nature which the standard model particles don't feel, and that's why we don't yet observe the 4th force. But maybe the dark matter actually experiences the other force. So people actually think the neutrino is almost there. It is almost dark. It just barely interacts, and we have managed to see it eventually. Suppose the dark matter interaction was due to this additional force, and the standard model particles don't feel that additional force. So how would we ever know? Indeed, you'd never feel with electrons and protons the dark matter because we don't feel the same force. So we are lucky that we can sense the electrons and the quarks and the neutrinos because they share at least one force. And it's because of the force that we can sense the interaction. So if they don't share a force, nothing wrong with that. So how would we ever see this dark world? It's very easy to actually imagine the Higgs connecting the different particles. So while it's very easy to make a theory of another kind of particle that doesn't experience the standard model forces and therefore is essentially dark to us, it's very hard to actually imagine that those particles don't experience the Higgs. Because everything in the standard model does experience the Higgs, and that's why it gets the mass. So what if the dark stuff, even though it doesn't experience any force shared with us directly, what if it also gets the mass from the Higgs? So the Higgs would be the thing that connects.
All right.
So does our Higgs do the job? And here's the beautiful idea. Suppose the dark sector has its own Higgs.
Okay.
And that's how you get 2 Higgses. There is the one that does
but why
for us.
Okay, but the question is, why is it only influencing the W? We need to reverse engineer the whole question and say, like, why that relationship only?
It's been done. So here's my quick explanation of it. It's a very good question because you got to ask, why doesn't it be visible here, there, and there, and why haven't we seen the effect already, and so on. Remember, it's the Higgs. What does the Higgs do? Its whole job is to interact with the fields, with the particles in such a way as to create the mass effect. That's what it's for. That's its job. So anything that's light is because the Higgs doesn't interact with it. Anything that's heavy is heavy because the Higgs interacts with it. Sort of natural logic, right? So that's why the electron and the up quark and the down quark, they're very, very difficult for them to sense the Higgs because they're light, and so they're not interacting with the Higgs. And that's why we couldn't make the Higgs for the longest time. Why did it take 50 years to make the Higgs? The Higgs only interacts with the heavy objects. So most of the experiments are done with electrons and light up quarks and down quarks and this and that. And they're all light. So what are the heavy particles? The W is one of the heaviest we've got. The top quark is the other heavy particle we've got.
Okay.
So these are the two that have a big interaction with anything Higgs-like, 1 Higgs, 2 Higgs. These are the two particles that have a big sensitivity to the Higgs. Okay? Which of the two heavy particles can we make precise enough measurements on to see a 0.1% effect? Not the top. Technical reasons, but you just can't do it with the top.
Right. Okay.
From all the standard model particles, I got you the two heaviest ones, which could sense the second Higgs, for example, or the additional Higgs thing, or the dark matter connecting Higgs or something. One of them is amenable to very precise measurements. The other one is not.
Mhm.
Which one do you think is the first one to get the precision to see a 0.1% effect? It's the one I chose.
Wow.
And that's the why I chose it. I mean,
Right. Okay.
in other words, if there was an expanded Higgs sector, if there was a sector that could talk to the dark matter, perhaps it's the Higgs associated with the dark matter, but because it has a Higgs-like property and we already have the Higgs-like property, so then they talk to each other, and that's how the heavy particles would know about this other world out there, the dark world out there. Who is going to be the particle that can sense that? It has to be something that has a strong Higgs interaction. And now your choice is narrowed down to the two heaviest ones. And then which one of them can you actually observe with that level of precision?
W. Yep.
That's why I chose it. That's why I've spent 27 years on it, and
Yeah.
maybe it paid off.
So
It's always like that, right? Why do you see something for the first time somewhere and it hasn't been seen anywhere else?
yeah.
In the end, you sort of backtrack and you say, aha, of all the places we were looking, this particular rule or this particular mechanism or this additional effect is the strongest in this place compared to everywhere else.
Right.
So, for example, I always go back to this Neptune thing.
Yep.
People by then had observed the orbit of Saturn, they had observed the orbit of Mars, they had observed the orbit of Jupiter, making lots and lots of measurements.
Mm-hmm.
Why were none of those looking funny? Why did all the calculations of the gravitational forces not showing up as a problem for explaining Jupiter's motion, Saturn's motion, Mars' motion? Hey, Uranus was the furthest one out. It's the one that occasionally comes closest to Neptune. If there was a Neptune, who do you think is going to affect the largest? Not Jupiter, not Mars. There's an even smaller effect on Jupiter and an even smaller effect on Mars. So if you keep measuring the Mars orbit or Jupiter's orbit very accurately, the effect there is so small, you're not going to see it.
Yep.
You should go to the place where the effect, no matter how small it is still the largest. So it shows up after the fact, you realize, shows up obviously the largest on Uranus.
Mm-hmm.
So whoever was observing Uranus is going to see the Neptune effect first. It's not like there isn't an effect on Jupiter, it's just that much smaller, and so you don't see it.
Got it.
That's my logic for the W. It's got a natural advantage
Yep.
in sensitivity. So this is what happens, right? We all think hard about if an additional thing was going on like this, if there was yet another mechanism in nature like that, if there was a second Higgs, if there was a dark matter connection,
Yeah.
we know something like this is going on. From which logical reasoning should it show up first as a deviation in the electron's property? or a deviation in the quark's property, or the deviation in the proton's property, or a deviation in the top quark property, or this or that. We can say, yeah, for these reasons, sure, you should measure the electrons very accurately. That kind of mechanism, best to do it there. This kind of mechanism, best to check over here. So everybody goes and does all these things. So which one do you choose? Well, you choose one of them, you place your bets.
Mm-hmm.
And maybe I bet right.
How much more measurement do we have, or do you feel comfortable doing with your teams, if any? Or are we at the point where now it's time to start to think about why is this delta here? What is causing it? Or do you even care about do you just care about the fact that you measured it at this point? Or
I would say the second thing you said. Let's directly explore the possible explanations of the delta. So let's go see if, according to the math, what kind of a second Higgs or what kind of a dark matter force or something. So look at those 200 papers and all those ideas.
yeah.
See what of those ideas have a common theme, which would say, look for another force over here. Look for this kind of reaction at the LHC.
Mm-hmm.
Or a second kind of Higgs ought to show up there, like the Neptune prediction, right? Look at the prediction and go check there.
Yeah.
Or is there some low energy experiment you can do with other particles, smaller scale or something? Start exploring those ideas and start checking every one of those out. My personal feeling, that would be better, sort of more interesting, more direct.
Yeah.
Now we know there is a mystery. Let's find the answer. It's like, we've got a prediction for Neptune. Let's go actually find the Neptune. That's Do I want to measure this delta more accurately than this? I have ideas. Of how it could be done even more accurately.
Okay.
Now, the second thing is, every time you get an idea to do something more accurately, you must also have more data. Once you run out of data, better and better ideas can't pay off anymore. It's like diminishing returns. Have to go together. Better ideas, more data sort of have to go together.
Okay.
Now, the Fermilab experiments are done. There's no more data coming out of there. So you can ask whether the LHC experiments have more data on the W itself. And the answer is yes, much more. So could better ideas be tried on the bigger and bigger LHC data to get the delta measured more accurately? The answer is yes.
Okay.
Do I want to do that? I feel like I want to take a break.
Oh, no. All right.
I mean, my ideas are published. Our ideas, I mean, my colleagues and I, we published them.
Yeah.
There's something to be said about other people trying our ideas on the data. It doesn't have to be us again.
Yeah.
I've done it 5 times. Doesn't have to be me again for the 6th time and the 7th time. Could be, but maybe I'll jump back in.
Yeah.
But there's something to be said for others, people learning from each other and adding on to the ideas of other people and extending it. So you only have one life and you have like 24 hours in a day. And so my current thinking, which could change tomorrow, it's only been 4 months since this one was published. Kind of what I'm in the mode of right now is people listening to our presentations, reading our paper. I have probably given 20 seminars at all the national labs worldwide, China, Japan, Europe, US. My fall semester is literally every week, next week, week after, literally all the way to January, February, every week is a colloquium or a seminar somewhere. So I'm traveling around all over. This is helping to get feedback from the community. Which of the all the logics and ideas and procedures we published, and I explain them more in person, sometimes better than in writing. What do people think about them? Do people think there could be some improvement that could be made or something like this? If I get a whole bunch of useful feedback like this and say, okay, I can see out of all of this 3 more improvements that could be made, and I could do them relatively quickly, or get a team together and do it once more, maybe. But on the other hand, if we sort of get the feeling from all these conversations, right? You give your presentation, you talk, and then you sit down after you're having coffee, dinner, lunch, and you're discussing, and you say, people are saying, okay, I buy what you're saying. I see your procedure. I now understand better than just reading your paper. And yeah, I'm not sure what could be done about it. Yeah, you might try this, you might try that, but I don't think there's much improvement to be made. If this theme comes up from all this months and months of discussions, then my answer to you 6 months from now would be, yeah, I've been having lots and lots of conversations, and it's not clear any major improvement could be done. So I feel like now it's time to go directly look for that other Higgs or the dark matter idea or this or this. Maybe I should. It's better that my time would be better spent this way.
Yeah.
So ask me again in 6 months, but my feeling is from the 5 months of discussion that I've heard so far, there are a few workshops I'm attending. In fact, 2 weeks from now, I'm going to Italy, Pisa, and Milan, and we'll be having lots of workshops there. Many other people are coming. There is one particular thing that I see should be looked into more. I mean, we looked into it, we published what we did. People are going to look at it again. It's not so much data related, but a calculation related thing. So everybody can check it out, so to speak. I'll check it out, others will check it out.
Yep.
We'll probably settle that action item in 6 months. There may be nothing there. There may be a small effect there. My feeling is this result is here to stay.
Got it.
So, short answer at the end. My feeling is I'd like to go check out second Higgs interacting with dark matter. How might you see the effect of the second Higgs showing up in the dark matter, something at the LHC. So
got it.
I have and I'll say one other thing.
Yep.
I've actually been thinking in parallel, but now I can really rev up that part of my research. I've got a sort of artificial intelligence type technology idea. I've published a couple of papers in the last 2 years.
Okay.
Back burner thing, but now I can make it 100%. And this is a way of processing the data at the LHC 100 times faster than what we can do at the LHC now. And why would you need to be that much faster? There are a particular kind of dark matter signatures that people have already calculated. You could observe it at the LHC, but not with the current information processing technology. The LHC electronics, computers, software, all that works incredibly fast. I'm talking million times per second, that fast. But the collisions are happening 40 million times per second. So there's that factor of 40 to 100. And anything that happens like dark matter that just comes and goes, right? It disappears before you can snapshot the picture. If it happens faster and in a particular way that all those other technologies cannot detect, there's a possibility that certain kinds of dark matter signatures are actually occurring in the LHC but we cannot record them fast enough.
That's sad.
It's, yeah, we've covered all the things you could think of. Can you observe every W boson produced, every Higgs boson produced, every top quark produced this? Do you have the technology to record that one, that one, that one, that one? Yeah, the answer is people have thought about 20 years how you could record all of that information. But there's always one more way nature could manifest. Oh my God, that one's a bit too fast. Can't see that one. Now, what if that's the one that's going on? It turns out that some of those things are particularly related to dark matter. So it's sort of coincidental and maybe not coincidental because it's dark matter. So some of those things could be escaping. So we need an even faster technology. So I've got an idea for that. That's sort of machine intelligence, AI based.
Okay.
And what I want to do is, instead of doing it with software, which is too slow for this particular thing, I want to embed all of that directly into silicon chips. And I'd like to get those silicon chips put right on the sensors so they can access the data as soon as the collision happens. Like literally 40 million times per second, they can record the digital picture and then process it just as fast, which is 100 times faster than the way we're doing now. And if it's that fast, it could record the particular types of dark matter signatures that people have talked about.
All right. Are you writing a proposal to CERN soon for that, or?
I have a team. I've written 2 papers which explain the mathematics. Those are out there, and people, I've talked about them at Snowmass, and people are reporting it and say, wow, if this would work, that's amazing. So why aren't we there at the proposal level? What I haven't published yet is a proof that the mathematics equations can be turned into a set of electronic circuit logics. So that's what a computer chip does, right? It eventually has to turn mathematics into circuit operations. So it's literally little circuits, electrical circuits, and they turn on and off and they transfer currents here and there. And so you have to map logical operations into circuit operations. So I need to show that the particular mathematical logical AI algorithm I've cooked up actually is implementable on a silicon chip. I think it can be done, and I think it will be fast enough. But the team I've got with my 5 or 6, actually there are undergrads, right? There are physics undergrads, math undergrads, computer science undergrads, and electrical engineering undergrads from Duke. 10 of them so far. They join the team, they work for a year or something, then they move on. This fall, we are working on a paper that will show an actual silicon chip implementation of the logic.
Okay.
So you can call it sort of an AI chip rather than AI software. It's actually an AI chip in a sense, designed for a very particular task. How to process the LHC images that we record so fast that this particular signature cannot escape. If it happens, we'll spot it. So ask me when this demonstration, actual proof of the chip implementation is published. Maybe 6 months from now. We're actually writing it right now. We think it works. But you know how science should be done, right? You write it down, you let people read it, you let them critique it, you let other people check it out, and they say, yeah, we think this actually works. This is right, this works. At which point it's ready for a CERN proposal. So 6 months from now, I'll be on the circuit saying, we can do this. Check out my paper. We can actually build these chips. Here's a cost estimate. It's not crazy expensive on the scale of our projects, on the scale of any science project. These chips are about $1,000 each.
Yep.
Advanced silicon chips. I estimate I need about 2,000 of them.
Mm-hmm.
So it's a few $1 million, maybe $3 million or something.
Mm-hmm.
On the scale of, a typical professor's research, the infrastructure sitting in a lab is usually worth that much.
All right.
The big national labs, their infrastructure is worth billions of dollars, $1-2 billion built up over a couple of decades.
Yeah.
But individual professors' labs, if you ask like somebody looking at AI or somebody looking at biology or somebody looking at protein folding or any of these chemistry things, usual professor's lab often has a few $1 million worth of microscopes and cryogenic equipment and like this. So scale, which is sort of as small as that, I think I can make this thing work. So
yeah,
that's the other half of my answer.
Yeah.
I think this could give us a really, really good sort of new functionality to observe things at the LHC, which we could never do before. So the thing you said, if you were producing dark matter and it's escaping, sad. We had it, we just couldn't catch it.
Right.
I can sort of sense the priority, right? That it's very important to deploy something that can catch it. So that's
Nice.
taking precedence in my mind over doing the W mass
Right.
delta measurement yet again.
Right.
Others can do that, but I better focus on this.
For now. Yeah. For now.
For now.
Awesome. Well, I think that's a good spot to leave it for this episode, but I'll definitely have you back to chat about some of that stuff when that's fleshed out. And me and you can talk for hours, so we better cut it loose now. But yeah, that's set it for that.
7:30.
Definitely. Yeah, we'll definitely chat about that when it comes up. Thanks for doing this episode, though. Excited to hear more about that. And any last words for the audience or anything that you're working on besides that, or?
I want to leave everybody with the feeling. So our field, because we are looking at more and more sort of laws of nature at the microscopic level, it always gets, you need the next level of technology, it takes time. These things are showing up in particle physics, major things after the Higgs and so on. Gravitational waves was a major thing. Now this, it's every once in a while. And you don't know what nature has in store. Sometimes people write funny articles like, after the Higgs, even particle physics over, we should focus all our energies on other sciences or something like that. There's so many mysteries still left, and now you get these tantalizingly strong clues, amazingly large delta here, some big puzzle over there, something doesn't make sense, dark matter is out there, mysterious thing. We just have to keep pushing with all our energy and our thinking. And nature reveals its secrets in funny ways. Don't go for the doomsday things that sometimes people say, right? I think that's very far from the truth. People are thinking hard, brand new ideas are showing up, brand new clues are showing up. So things like this make me think another revelation level things around the corner, like things happened in the past. 100 years ago, 50 years, people thought, okay, we've nailed it. Now we've understood it. And suddenly you get some amazing surprise and you say, what? This makes no sense. There's a whole new world down there. So let's not underestimate nature. It's got plenty more to tell us. We just have to keep looking.